Hi and welcome to another electricity lesson. We're looking at internal resistance and I'll start immediately explaining what it is. Okay, if we had a circuit, that's a bit big. There we go, this is better. If we have a circuit and in this circuit we have an open switch, so the switch is the circuit is not closed, but there is a voltmeter reading over the battery. That voltmeter reading is called the EMF, and the little symbol that we're going to use for that looks like this, almost like an E, but that stands for EMF, electromotive force. Electromotive force, and that refers to the amount of energy that every coulomb of electrons have when they move from the negative end to the positive end of the battery. Okay, but then we notice something curious. Okay, and this is measured in voltage. Okay. The moment we close this up, if we close this, our EMF changes. Okay, or not our EMF, our voltmeter reading changes, which it doesn't change by much, it just changes slightly as it passes through the circuit, which means that we are losing some volts. Okay, so EMF is the absolute maximum voltage that the battery can supply, but as soon as the circuit is closed, we see, oh, we are losing some volts. So there is EMF, the maximum voltage that can be supplied, and then there is voltage that's given to the external circuit here, and remember, voltage is the amount of energy per coulomb. So in the external circuit, that's the amount of energy that is being used in this external circuit. Okay, used, or let's say external, but then there's some voltage that's lost. I should actually write it on this side, minus voltage lost, but let me just write it here, voltage lost. So the total volts that the battery can supply is given to the external circuit, but some is lost for some reason, and the theory is that it is lost by the internal resistance of the battery. So you'll notice that now, from now on, we don't just have a normal battery. What we're going to do is say, here's our battery. We're going to represent it like this. Here's our battery, but inside our battery, we have a little resistance. Now, you'll notice that this is in fact true, that when you have a circuit like you have a toy or something that works with batteries, and you'll notice that after you've used it, that battery is hot. Now, that can only be possible if the chemical energy in the battery is converted in the battery itself into something else, in this case heat, which means that it must have resistance. A resistor is something that changes electricity into another form of energy, and so a battery itself contains some internal electricity, so that when internal resistance, so that when the circuit is closed, that is lost. It cannot be used in the outside of the circuit. Okay, now if I were to multiply everything here with or rather not multiply, divide everything with the current, the total current. Okay, so total current, everything gets divided with the total current. I can do that in an equation. That's definitely allowed, to divide everything. Okay, so does the total current flow through the total external resistance? Well, of course. Okay, does the total current flow through the battery? Well, of course. Okay, all of the current passes out and into the battery, which means all of the current passes out and into the internal resistance. So I do this because according to Ohm's law, we have that current is equal to volts divided by resistance. So if I have volts divided by resistance, I get resistance. Okay, so this here represents the total resistance. This here represents the total external resistance. Okay, so that's the resistance offered by everything except for the internal resistance. And then this represents internal resistance. Let's do it like this. Internal. And for simplicity's sake, external resistance will just be represented with a capital R, and internal resistance will just be represented with a lowercase r. So the total resistance is equal to the external resistance plus the internal resistance. That's not very complicated, okay? But once again, if I were to calculate EMF in calculation would be according to this total volts. EMF is the absolute total volts that the battery can supply. That is the product of total current times total resistance. So total current times total resistance, and total current times total resistance, sorry, that must be a T, total resistance is R plus lowercase r. So this here, EMF, this is a very common formula that we will use when working with internal resistance in questions. Alternatively, we can also multiply in, and that's when we'll get to the EMF is equal to the current times the external resistance plus the current times the internal resistance. That's also a common formula that may be used. Again, it all just follows from Ohm's law. So don't go and try and remember these formulas. It follows from Ohm's law just with the fact that total resistance is the external resistance and the internal resistance. One more thing, another word for external resistance is called load. The load is a name used for the external resistance in a circuit. So just a brief recap, okay, the EMF is the electromotive force. That's the absolute maximum voltage that a battery can supply. We can measure the EMF very easily by just measuring the potential difference over the ends here. In other words, with not closing the circuit, we have the internal or the EMF. The moment we close the circuit, we then notice that there is a difference in the voltage meter reading. That is because inside the battery we are now losing volts. Okay, that's called lost volts. And so we get a voltage, in other words, the energy spent per coulomb in the external circuit. That's external voltage, and then volts lost is the energy spent by the battery itself per coulomb. Now the total resistance is simply the sum of the external resistance and the internal resistance. External resistance is sometimes called load, and then we have these two neat little formulas that make calculations actually very easy. Well, I hope this was helpful. In the next few videos we'll look at some examples of internal resistance affecting a circuit. We'll see you there.